Okay, welcome to lecture here. We'll get started here in just a second. We're off to chapter 10, I believe. So that should be where we're off to. So we have chapter 10 and chapter 11, and then I think that's all they wrote. And it'll be all over at that point. Um, so again, these notes should be up online if you need them, where all the other notes are found as well. All right. So we'll get started here. And in this chapter, we're going to talk about solutions, obviously. We're going to talk about some aspect of solutions, some of which we've sort of covered a little bit along the way in some other chapters. So we'll probably just kind of go over that stuff a little maybe quicker as sort of a review. And then we'll get into some new stuff that we have not talked about, perhaps. So let's start with sort of liquids and sort of solubility. So a lot of times when we talk about solubility, um, we oftentimes sort of think about it in the sense of a solid dissolving in a liquid, for example. So if you take an ionic solid and you put it in something like water, it will dissolve. And we oftentimes think about it in the sense of it's soluble because it does dissolve and sort of the solid disappears. Again, it doesn't really truly disappear or anything like that. It just gets sort of wrapped up with the water, and the water basically surrounds it. Now, when we talk about solubility, sometimes when we talk about liquids, for example, and liquids sort of mixing with other liquids, we talk about it in terms of being miscible or immiscible. And really, they really do run along the same lines as soluble or insoluble. So if two liquids mix completely, they're soluble in each other, and they're said to be miscible, and something like ethanol and water would be soluble in each other or miscible. And if you did take, for example, two liquids and put them into a test tube and they were miscible in each other, basically it would all look the same throughout. It would all dissolve, look like one liquid, basically. Nothing really would dissolve since they're liquids. It would just look like one liquid that was in there. And again, what makes things able to be sort of soluble in other things or interact well with other things is a lot of those intermolecular forces that we talked about in the previous chapter. Forces like dipole, dipole, hydrogen bonding, dispersion forces, and so forth. So when we look at something like ethanol, for example, ethanol looks something like this. Do some fine drawing here. Pop a couple of hydrogens. So this guy here is ethanol, and hopefully you also recognize water. And what we know about water is it's polar. And again, essentially what that means is overall water has a side that's more positive and it has a side that's more negative. On water, it is the oxygen side there that's more negative. The hydrogen side is more positive, again, because of that polarity. Now, although the carbon hydrogen part here of ethanol is pretty much, kind of put a box around it, everybody here in the box is carbons and hydrogens, which is essentially a nonpolar bond. But it does contain an OH bond, and that bond is going to be a polar bond, which means the oxygen there is going to be partially negative. The hydrogen there will be partially positive. And that's what's going to allow, for example, the hydrogen in one to be attracted to the oxygen in, say, something like water. And that's what's known as the solute-solvent interactions, and those are hydrogen bonding. And because they both basically have the ability to hydrogen bond, they're actually very, very soluble in each other. And they would be considered miscible in each other because they're basically replacing water and water interactions with similar interactions that we find in water with those hydrogen bonding. Now, if we take two liquids and they really don't mix together, and they're sort of, if you want to think about it, insoluble in each other, they are said to be miscible in each other. or sorry, they're said to be immiscible in each other. Get that word right there. So when two liquids really don't mix, they're said to be immiscible in each other. And if you did put two liquids that really don't mix in a test tube, you will end up seeing different layers. So perhaps you remember when we were in person this semester, we did that experiment way at the beginning. I almost think it was experiment 4, maybe, or 3 or 4. But where we mixed the hexane, for example, with the halogens and so forth, and we had sort of different layers. So you will definitely see these sort of layering that will happen when you put two liquids in a test tube, for example, that really don't mix. And carbon tetrachloride, which is CCl4, and water are immiscible with each other. And that's because when those two guys get together, unlike what we have up here on top, if we take carbon tetrachloride and draw the Lewis structure, you should recognize that this is a symmetrical geometry where everybody attaches the same. And what that essentially means is our good friend here is a polar molecule. And our water here also going to be a polar molecule. And the problem is when they try to interact with each other, they're not going to be able to interact with each other over the long period of time. Really what CCl4 is going to want to use, he's going to want to use those dispersion forces. While water here is going to want to use some hydrogen bonding. So for the short period of time, they can sort of interact with each other through sort of what are known as those induced dipoles. So induced dipole, and dispersion forces. Remember, this induced dipole means that basically somebody with a charge, either a polar molecule or an ion, gets next to somebody that has nonpolar and basically distorts their electrons, basically their electron cloud, and creates that sort of temporary attraction that occurs. So again, if you did have for the short period of time, we'll call this our sort of CCl4. We'll have our water, which is polar. Again, for a short period of time, what's going to happen if he's near it, he's going to induce these electrons to run the other way. And again, that's going to create this guy that normally would not have a charge gain that temporary charge, which is that induced dipole. And at that point, I was going to actually this guy, they would have a way to interact with each other. But again, it's only really a short-term sort of interaction. And if you leave it alone, again, almost like oil and vinegar salad dressing, you can mix it really well. Everything's going to look nice and mixed, right? But if you put the dressing down, the bottle of dressing down, if you look at it a little bit later, what you see is pretty much everybody separates out from each other. You see the kind of the oil part go to the top, so the aqueous water part go to the bottom, and you see definitely some different layers. So again, for the short term, they could sort of interact with each other. But over the long haul, they have no real long range way to completely sort of interact with each other. And again, that usually will lead to something being immiscible and those distinct sort of different layers that you see. And it really does bring up that idea that I think we've talked about before, but just to reiterate, this idea of what is known as like dissolves like. So things that have similar intermolecular forces are very soluble or miscible in each other, while things that have very different intermolecular forces, they typically are insoluble or immiscible in each other. So when we talk about like dissolves like, you know, in terms of solubility, typically you're good if you got a polar and a polar thing. You got an ionic guy and a polar guy coming together. If you got a non-polar guy and a non-polar guy together, that's all good. But really, for the most part, in terms of insoluble or immiscible, is when you cross over there and you try to put your polar and your non-polar guy together. that's where you're going to run into trouble. And again, that's what we're talking about here in the middle. You're going to end up with something that's going to be immiscible and really not mix. Any questions on that? Again, a reminder, if you do have questions, feel free to type them in. I'll be happy to answer them for you as we go through. So here's just a couple of pictures here, A and B. I wish I knew what they were, but again, I don't remember. But we do see some distinct layering happening here. And again, these guys would obviously be immiscible in each other. And this could be like with that experiment we did. Remember, the top layer then went and changed color to the bottom layer. And but we do still see distinct layering, which would imply again that these things would be immiscible in each other. They definitely do not mix. Now, when we do talk about sort of the solubility of solids and sort of water, or solids and sort of a liquid, usually, again, we move away from miscible and immiscible to being soluble or insoluble. So as I talked about before, ionic substances, sodium chloride, ammonium nitrate, anything that's sort of a cation, anion type of situation, those things are definitely usually very soluble in things like water. Again, because they're going to do that ion dipole interaction that we talked about. The positive cation will be attracted to the negative side of water. And basically the water molecules will surround it when it goes for a swim. And it would surround it with the oxygen, which is again more partially negative. While when the anion goes for a swim, it also gets surrounded by water, but it actually gets surrounded by the hydrogen side of water, which again, the hydrogen side of water is the positive side of water. And if you remember, basically all these sort of intermolecular forces, basically they all root down to electrostatic attraction. And that basically is your positive and negative attraction to each other. And that's essentially what we have here. Again, this would be something like an ion dipole interaction. And this is really how some type of ionic solid really does dissolve. So when you take an ionic solid, like some sodium chloride, and you put it in water, essentially those ions will break apart. And this attractive force between water and those ions basically surrounding each of those ions. The water basically does two things. A, it basically helps sort of in our eyes when we look at it, we dissolve something, it makes it appear that it's gone, it disappeared, right? It's gone. And really, again, the sodium chloride hasn't disappeared. It hasn't really gone anywhere. It's actually still there as sodium ions and chloride ions. The only difference is we really can't see it because, as you kind of see in this picture, it gets surrounded by water all the way around, and that helps it sort of dissolve. It also prevents these two ions from coming together. So when the water sort of acts as a buffer to prevent the positive ion and the negative ion from wanting to come back together, remember that those guys definitely would want to come back together because that is an intramolecular force, which is very strong. So when an ion, positive, negative guy are near each other, they do definitely want to come together. But the water prevents that from happening. It keeps them apart, and it also helps it sort of dissolve. That's also why if you've ever taken some sodium chloride solution or salt water and you heated it up, when you start to heat it up, what eventually happens, obviously, as you're heating, is you're going to start to evaporate off the water. And as you start evaporating off the water in this scenario, waters start to go away, waters go away here as they evaporate. And before you know it, there is nothing in the way of these two ions coming back together. And they will come back together, and what you will see is your ionic solid back in its original form. It will come back together as a solid because you evaporated off the water. So ionic substances are very soluble in things like water because they could do sort of that ion dipole interaction. They basically can interact very well. Sugar and ethanol. So ethanol is that molecule we just saw a second ago. And as we were just talking about, again, ethanol, because it does contain this one little polar bond between the oxygen and the hydrogen, it's able to interact well with water through hydrogen bonding, which, as we talked about, is a very strong intermolecular force. So hydrogen bonding is sort of the strongest, dipole, dipole the next, and the weakest out of all of those is those dispersion forces that we talked about. Now, sugar is a little bit larger of a molecule, but one thing, as we will see in sugar in just a second, is when you look at sugar, it is loaded with all these OH bonds all over it. And because it contains all these OH bonds, that makes something like sugar very soluble in water. Even though sugar is basically carbons, oxygens, and hydrogens, that's all covalent bonding and all that kind of stuff. But it does contain a lot of those OH bonds, which are polar. One side is positive, the hydrogen, the oxygen side is negative, and allows it to interact with water very well. Solubility does decrease, by the way. So if you took something like ethanol here that we had in the box earlier, and if you basically build out the carbons and hydrogens, so you just kept adding carbons and hydrogens attached to all of them, the solubility will decrease a lot. So if you build out about 6 carbons or so, even though it still has that OH group, the solubility of it in water will drop tremendously. And basically what happens is the molecule kind of gets too large. So when you build out all those carbons and hydrogens, you got this really big part that's nonpolar. And the only part that you got over there is this kind of small, I'll draw it like that, polar part in something like that, like when you build out the carbons and hydrogens. And kind of this part here gets in the way of it being able to interact well with water. So it really does decrease the solubility. Ethanol is an organic compound, and usually it's an alcohol because it has an OH group. And usually alcohols of about 6 carbons or less that have that OH group are very, very soluble in water. But again, as soon as you build out more carbons, the solubility does decrease a lot as you go through it. So here's just a couple of examples. This is methanol. Again, this part is really non-polar. That's a very bad arrow. But again, it does contain that oxygen and hydrogen bond, which is a nice little polar bond. So again, this being negative here, this guy being positive, positive on our water, negative, again, able to hydrogen bond, which is our intermolecular force. And again, increasing the solubility of it. And there's our ethanol in a nicer picture. So when we do take something, for example, like oil, and oil also is made up of carbons and hydrogens, but essentially that is all that it is made up of. So oil is typically a very long chain of carbons attached to carbons, and those carbons have hydrogens on them. And that's pretty much non-polar all day. So it's a big giant thing that is non-polar. So again, water is insoluble in water, non-soluble, I guess insoluble is a better word there. So oil is insoluble in water. And again, it really is for a couple of reasons. Oil is non-polar. So again, it's going to want to use dispersion forces. While again, our water, which is polar, is going to want to use hydrogen bonding. So again, over the long period of time, they have no real good way to interact with each other. And if you've ever seen like pictures of perhaps like an oil spill in the ocean or whatever it may be, you know, what you typically will see is the oil will start to float on the water. And again, it's because it can, for the short period, again, be able to interact, but over the long haul is not able to maintain those interactions and really will sort of separate out from each other. Another problem with oil and water is in order to basically replace something into water or put something into water, before you do that, you essentially have in water, right, all these water molecules that are bonded to each other through a network of hydrogen bonding, right? So before you dissolve something in water, you got all these water guys basically bonded to each other. And basically, to allow something to dissolve in water, you got to break apart these water-water interactions. And you do need to replace them with something that's very similar. And that just doesn't happen with oil because, again, it's trying to do dispersion forces, water trying to do those hydrogen bonding. In addition, oil is usually a very big molecule. It doesn't fit very well with water, which is sort of a small molecule. So you would have to make a big giant hole in this sort of water-water interaction to allow room for it. And, it's not going to fit so well. You might be able to get a little bit of it in there, but over a long period of haul, it's not going to fit. So for example, if you took like a bus, for example, that was small enough to get into a garage, yeah, you could get some of the bus into the garage, but it's probably going to hang out the back end. Hopefully it doesn't rip off the roof of the garage, but we'll just assume we could get in height-wise. But length-wise, maybe a limousine would be a better example. If you try to put a limousine into a normal garage, you could get most of it in there probably, right? But the back end probably would hang out. And it just doesn't fit really well in sort of that opening. And it's sort of the same idea with water. Oil is such a big molecule that, you'd have to bury a big giant hole in water to get it to fully sort of incorporate. And it just doesn't happen. Because it really doesn't have the interactions to allow that to do that. So again, back to this idea of like dissolves like. So things with very similar intermolecular forces are always going to be pretty much soluble in each other. But things that have very different intermolecular forces, and for the most part, that usually means you're trying to take something nonpolar and polar. Those are pretty much your differences there. They really won't interact and be insoluble in each other. Any questions on that? Now, depending on these sort of interactions, we do get some properties of parts of molecules. And sometimes some parts of the molecules are what are referred to as being hydrophilic. Hydrophilic means that it is water loving. And that usually, again, means that that molecule has some type of region. It may not be the entire molecule, but there's some area on that molecule that is able to interact well with water. So in the case of ethanol, again, as we've seen this picture a couple of times already here, this part again in the box is nonpolar, so that's not going to interact very well with water. But because it does contain this region that is polar and does interact well with water, that region of it there would be the hydrophilic region, the part where water would interact. Now, there are some parts of molecules that are also known as being hydrophobic. And hydrophobic basically means that it does not like water. And it has usually, for example, a region like we have in the box there that is nonpolar, all carbons and hydrogens sort of together. And it doesn't truly like water. So soap is another example of that. Soap, for example, and I won't draw it all, but basically soap has two regions as well. You got this really long carbon region, and all these carbons, and again, I won't draw all the H's on it, but they all have H's up and down all the way across. And at the end of soap, you have this region over here, which is based off of carboxylic acid and organic chemistry. So soap basically has two regions. It has this region over here, which is the nonpolar part, sometimes referred to as the nonpolar tail of soap. And it also has this region over here, which is polar, and sometimes referred to as the polar head of soap. And really, soap has these two regions. The nonpolar tail is hydrophobic, does not like water, while the front part does like water. And that's really good because when we do use soap, that allows soap to be very sort of useful, if you will, because for the most part, most dirt and oil and all that kind of stuff is nonpolar. So what happens when you put soap on is the nonpolar part of soap, I'll just draw the carbons like that, basically surround it, very badly drawn here. So let's go all the way around. We'll just zoom. So the non-polar part of soap basically surrounds it and traps all the dirt on the inside. And on the outside, it puts its polar part. And that's good because the dirt's trapped by the non-polar part, which means they will interact really well with each other and be able to kind of trap it there. And then on the outside, we have the polar part, which is hydrophilic, which is good because typically when we do use soap, the next thing we do after we soap up is we wash it off with water. So when you go to wash it off with water, just do our generic water circle here, it's going to mix really well with the polar part of soap. And what will end up happening is the water will mix with the polar part of the soap. The soap is already mixed with the dirt, which is non-polar. And when you wash it off the soap, you're washing off the dirt as well. And you basically feel clean. It's good to know how soap works, I suppose. Yes. Here's a couple of pictures of when we mix octane and CCl4. Octane, which is 8 carbons all together with all hydrogens. So again, octane here is non-polar. CCl4, as we talked about earlier, also non-polar. So you can see when we put them together, everything mixes really, really well. We take gasoline, which again is non-polar. All carbons and hydrogens together. We got our water, which is polar. And again, they do not have a way to interact well with each other. And you can see here, we actually do see some different layering basically starting to happen. So let's just talk a little bit about solubility. When one substance, again, is dissolved in another, so the solute dissolves in the solvent, is said to be soluble. So salt is soluble in water. When one substance doesn't dissolve in another, it's said to be insoluble. So oil would be insoluble in water. Now, there is a limit to the solubility of substance. Again, you could take sugar and it will start to dissolve. Take some sugar and water, it will dissolve. At some point, if you take a giant box of sugar and just keep dumping it into, say, a cup of water, at some point, the sugar will stop dissolving, right? So solubility's limit is based usually on temperature, and usually at higher temperatures, you can get more solid in a liquid. At lower temperatures, there's less solubility of that solid in a liquid. But there are things that are usually always sort of soluble in each other. Gases, for example, are always soluble in each other, and that's because basically gases are just constantly flying around. So because they're constantly flying around, and if you have multiple gases, obviously in a container, they are flying around each other, which means they are constantly mixing. And by definition, that would mean that they are soluble in each other. Now, some liquids will also be mutually soluble in each other. So these are the liquids we were talking about earlier. If you take a polar liquid and a polar liquid, they will mix really well. If you take a nonpolar and a nonpolar liquid, they will also be soluble in each other. Again, it's just problematic if you try to cross those two. If you take the polar and the nonpolar guy and try to put them together, then you're going to run into a little bit of a problem. As I mentioned, temperature does play an important sort of role in terms of solubility. And the higher the temperature, for example, we typically will have a larger solubility of a solid in a liquid. And remember that when we increase the temperature, what we're essentially doing is increasing the energy. And that increase in energy is going to allow, for example, that solid to sort of break apart a little bit more. It's also going to allow a lot of the, for example, water molecules or something like that to sort of move around faster, have more energy, be able to pluck off all those sort of solid ions and help it start to dissolve. When we lower the temperature, for example, we have a larger solubility of a gas in a liquid. So, for example, we have our gas molecule here. And if it's at a high temperature, it's got a lot of energy, right? So it can kind of move around, jump out of the glass, hopefully not, right? And it can move around very, very fast. But if we lower the temperature, it's obviously going to start to be moving a lot slower. So as it's moving around a lot slower, it is going to be in the liquid part for a longer period of time. And that's going to make it more soluble in the liquid part because it's not obviously moving out of it very, very fast. Now, when we talk about gases, pressure is an important aspect of that as well. And the higher the pressure, the larger the solubility of a gas is. And if you remember, pressure and volume are related to each other. As one goes up, the other goes down, and vice versa. Which means if we increase the pressure, we have just decreased the volume. And that means that the gas molecules will be closer to one another. They won't be moving around as far from each other. They'll be in a very small space, which means just by that sort of definition, they'll be mixing a lot more. Kind of like what we talked about there when we talked about real gases, right? So if you remember, real gases at really high temperatures and really high pressures and low temperatures, they interact a lot more with each other because they're basically near each other a lot more. And here's just a prettier picture of what I drew. But again, you can see as you do this sort of dilution process, water molecules basically come in and pluck off all these solid, this green and sort of gray guys here. This would be like an ionic solid, again, in a very organized fashion, like we talked about in the last chapter, in that crystal lattice, water molecules moving and they start plucking it off. We also sometimes, when we want to dissolve something, we typically will start to stir it, right? So we'll stir it and that it will help it dissolve. And that helps it dissolve for a couple of reasons. It helps it dissolve maybe a little quicker because we're now basically splashing water all over that solid. So greater surface areas coming in contact with the water. And that's going to help it start to dissolve a lot quicker. In addition, the act of stirring is adding energy, right? So that's going to provide a little bit more energy to everybody and sort of help the dissolving process start to begin. And there's sort of our interactions, much prettier picture. But again, our sodium ion, which is positively charged, attracted, as you can see here. Maybe red is the bad choice there for a color. Let's try a different one here. To the negative side here of water, which is the oxygen. And again, going to surround each of these ions and help them dissolve. So let's talk a little bit about some of these properties of solution. There is a limit, like I said, to how much solute you can get to dissolve in a solvent. Remember that solute and solvent are the two parts of a solution. The solute is the smaller part of the solution. The solvent is the larger part of the solution. And when you put both of those things together, that gives you the actual solution. So again, just a reminder, this is the smaller part. And our solvent is the larger part of a solution. So what happens if you, for example, take way too much solute and try to dissolve it? Well, at some point, you're going to basically reach what is known as a saturated solution. And in a saturated solution, basically what that means is at that given temperature, you pretty much have hit the point where you have hit the maximum amount of solute that will dissolve. So once you hit that saturated solution, you're basically right at the point where if you decide, I want to try to dissolve more of the solid, if you go and put the solid in a saturated solution, it will stop dissolving and it basically will just start piling up there on the bottom. And that was sort of like the example I mentioned about the sugar. Again, if you start dissolving sugar packets, for example, it will start to dissolve. But again, if you dump like the entire box of sugar in there, at some point, it will not dissolve all that sugar. And it's hit basically a saturated point when it has stopped dissolving. Now, what's the opposite of that? That's the part where you have not reached that point yet. So that is a unsaturated solution. And in an unsaturated solution, That is where you have not hit that limit. And that means that if you take more solid, it will continue to dissolve. And it will continue to dissolve until basically it hits a saturated solution. So if you have an unsaturated solution, you could continue to put solid in it. And at some point, it will hit what is sometimes referred to as its saturation point. And when you hit that saturation point, you probably have now made a saturated solution, and then it will no longer dissolve. But up until that point, you can continue to dissolve the solid until you hit a saturated solution. Now, there is another type of solution, which is sometimes what is referred to as a supersaturated solution. And a supersaturated solution is a solution that basically contains more solute dissolved in the solution than it should at that particular temperature. So one way that you can sort of make a supersaturated solution is, for example, you can take a solid and put it in here and make a saturated solution. And then what you could do is heat it up a little bit. You could actually put a little bit more solid in and it will start to dissolve. Again, as we heat it, we're increasing the temperature. We're going to increase the solubility of that solid. So you actually can kind of pile in here a little bit more. But a couple of things is going to happen here as you're heating in and getting more of this to dissolve. You will eventually stop heating. And through the process of heating it, you are going to lose a little bit of that water, right? So you're going to lose a little bit of that water, which is your solvent. And if you let it cool down, what will happen at this point is you will now have a solution that has cooled way down from the heating process. And at that lower temperature, it should not have as much of that solute dissolved in there than it already does. So at this point, you heated it, you lost a little bit of the solvent. You also were allowed to get more solid to dissolve than should at a regular temperature, like room temperature. And now as you let it cool back down to room temperature, you have a solution that essentially has too much solid dissolved in it. And this is an unstable solution usually. It is so unstable that you literally could just tap. That was my sound effect there. You could just tap the test tube, and that could be enough to cause all of the solid to basically come out of solution. It's so unstable. But most of the time what people will do in sort of this experiment is they will then take like that little bit of the solid and drop it in. And as soon as you drop that one little seed crystal of that solid that's ready dissolved in there, the solution is going to realize, whoa, we have way too much solid dissolved in here. And what you will see is kind of neat. You'll start to see all of the sun, all of the solid will slowly work its way out of the solution. And you will go from a solution to a solid in the matter of sort of seconds. So you'll have this solution, it's liquid. You drop this one little crystal in there of what you dissolved in it. And because it has way too much solid in there to begin with, it's going to cause all of that solid basically to come out of the solution. And you'll end up with really a rock hard sort of solid. And that's sort of what this picture shows. This is probably something like sodium acetate. And this is a supersaturated solution of sodium acetate. And you can maybe barely see, they just dropped like this small little drop. And you can see as soon as it hits and goes in, right, it's going to drop in. Right where it kind of drops, the solution goes, whoa, I have way too much dissolved in me. And you can start to see it starting to come out of solution, the solid. And you can see it gets bigger, obviously. until finally you are left with this guy at the end. And that essentially is, at this point, pretty much a rock hard solid in there. So these supersaturated solutions is basically a solution that has way too much solute dissolved in the solvent at that temperature. It's usually a very unstable solution. I've actually done this experiment where I've accidentally just tapped the flask on the bench, and just that tapping of the flask, it's enough to initiate this whole thing to come out. You don't even have to add a crystal. So sometimes it's a really, really unstable solution because it really doesn't want to be that way. It wants to, that solid wants to come out, but you just sort of forced it to be dissolved. And unfortunately, it's going to be super unstable in that case. Any questions on that? So let's talk a little bit then about pressure and solubility of gases. And when we have external pressure, has an effect on the solubility of a gas. And Henry's law is a law that says the solubility of a gas in a liquid is proportional to the pressure of the gas over the solution. And this is Henry's law over here. The C is concentration and molarity. K is Henry's law constant and is different for different substances, so it's a constant. And P is the pressure in atmospheres. This is basically what describes what happens with our soda cans, for example, right? When you have a can of soda, it is basically water with a whole bunch of other stuff in it. And it also has CO2 gas, right, dissolved in it, carbon dioxide. And when the can is sealed, that thing, wow. That's a quick lecture. Let's go back. Hang on a sec. Come here. All right. Mind of its own. So when this thing is sealed, it's under pressure. And obviously when you pop the top of your can, that's going to release the pressure. So when it's sealed, all the CO2 is dissolved in the water part. When you pop the top, you release the pressure and all that CO2 runs out, right? And that's what you see, right? When you open the can, you got all that fizzing that's coming out. It's like all that CO2. In addition to releasing the pressure, you also provided the gas an escape route, right? To basically leave. And that is also why what happens when you take a soda can and you open it and you come back to it a while later and you take a drink of it and go, that's not so fresh anymore. That's because it's gone what we like to call flat, right? Pretty much you've opened the hatch, you decrease the solubility of the CO2 in the liquid part. You also gave it an escape route out the top. And basically there's not very much CO2 in there. So you basically got, water and sugar in there. Basically it doesn't taste so good because it's kind of flat. These are some Henry's Law constants, not from your book, but you would have a similar sort of table in your book where you could look them up. Again, they are different values depending on the gas you're dealing with. So much like anything else in the table, you want to make sure that you look it up for the correct gas. You also want to make sure you look at the units in those tables. Here's a much better picture than my soda can, but again, before you pop it, you got all that CO2 basically in the liquid part. It's under very high pressure at that case. That's going to keep all that liquid, all that gas in the liquid part. Again, as I said, you're going to alleviate that pressure when you pop the top and also give the gas a much needed escape route out the top, and sadly leaving us to our flat soda at some point. So let's take a look here and see if we want the pressure of CO2, what pressure of CO2 is required to keep the CO2 concentration at 0.12 molar at 25 degrees Celsius. So we could use Henry's law here to help us with this calculation. And if we look it up here, again, this would be Henry's law's constant for CO2, which would be in that table. And some books will not use C, but some books will use S for solubility. And that really is the molar solubility, which is a lot of words just to get you back to, that's the same thing as molarity, really. So sometimes people will use that S, and really what it stands for is molar solubility, but really what it stands for is molarity anyways. So in this case, we pretty much have everything we need. We can rearrange Henry's law and solve for P. And if we do, P is equal to S divided by KH. And if we put our numbers in there, we need to keep the pressure in the soda can at 3.5 atmospheres. And that is a pretty good pressure, because remember, sort of atmospheric pressure and standard pressure is 1 atmosphere. So that's like 3.5 times greater than atmospheric pressure. We need to keep that soda at, to keep all that CO2 dissolved in the liquid part, keep our soda fresh, if you will. Any questions on that calculation there? Okay. So let's just talk about some of these units, which I think we covered in a previous chapter. But let's just make sure. This is percent mass by mass. This is 1 unit of concentration. Percent M/M is sometimes referred to. And it is the mass of the solute over the mass of the solution. And it is the bottom part that's really important here. Again, and sometimes in these problems, they will give you both of those values separate from each other. So they'll give you the mass of the solute separate from the mass of the solvent. And it's very, very common that people will just use the mass of the solvent on the bottom and not actually the solution. So a lot of times in these problems, you do need to sort of add those values together. There's also some other percent units. There's percent volume to volume, and that is the volume of solute over the volume of solution times 100%. And there's also percent mass to volume, which is the mass of the solute divided by the volume of solution times 100%. So if you did have a 4.5% mass to mass sodium chloride solution, that would mean you have 4.5 grams of sodium chloride in 100 grams of solution. Or you could say that you have 100 grams of solution in 4.5 grams of sodium chloride. So if you're given the percentage by mass or percentage by volume or percentage mass to the volume, you could kind of turn those percentages into a conversion factor and use it as such. So here, if we look at this example, a solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. What is the mass percent? Here, our calcium chloride, which is the smaller part of the solution, would be the solute. Our water here would be the solvent. So water is a very common solvent. Not in 100% of the time is it always a solvent, but it works really well. And if we wanted to calculate the percent mass to mass, we would take the mass of the solute divided by the mass of the solution times 100%. So to get the mass of the solution, we would have to take the solvent, which is 2.5 grams. We would have to add it to our solvent, which is 50 grams. And that's going to give us a mass of a solution of 52.5 grams. So to find the percentage, mass to mass, that will be 2.5 grams divided by 52.5, not 50, times 100. And we will end up with 4.76%. And again, most people will just write M/M to indicate that it is mass to mass percent. And again, you can use sodium chloride. Any questions on that calculation? So why don't you try this one? A concentrated hydrochloric acid solution contains 37.2% by mass. What is the mass of HCl this contain in 35.5 grams of concentrated HCl? So why don't you take a moment or two and calculate that? All right, so a couple of different ways you could do this, but we are doing percent mass to mass here. So again, that's going to be the mass of the solute divided by the mass of the solution. Times 100%. So we have the mass percent, which is 37.2. We have the mass of the solute. I'm sorry, we have the mass of the solution, which is 35.5 grams. And we're looking for the mass of the solute. Remember that the solute is usually the name of the solution. So if you're asked to find how much HCl there is in an HCl, kind of concentrated HCl, that means HCl is the solute, and obviously 35.5 would be our percentage, our grams of solution. So you could do it dimensional analysis way if you like. That's 37.2 grams of HCl and 100 grams of solution from the percentage. Or in 100 grams of solution, there is 37.2 grams of HCl. So if you want to kind of take a dimensional analysis approach, you could use it like that, 35.5 grams of solution. We would use a conversion factor on the left there, and that would give us 100 grams of solution over 37.2 grams of HCl. Grams of solution would cancel. 13.2 grams of HCl in this particular case. You could also plug and chug into the formula there, and when you rearrange the formula and solve for the mass of the solute, you're essentially doing the exact same math there as what we just did. So you can do it either way. They both will get you to the same answer. Any questions on that? Now, I think we talked about molality, I think, towards the end of one of those chapters. But just to make sure, molality is another unit of concentration for solutions. Molality is abbreviated with a small m. So small m. And that is the moles of solute over the kilograms of solvent. Again, not to be confused with, I'll make it big M, which is molarity, which is moles of solute over liters of solution. So this is molality. This big M is molarity. So again, not to be confused. So much like other things, molality is important. it is the moles of the solute over, again, just the kilograms of the solvent. So if we look at this here, we want to calculate the molality of a solution that's prepared by dissolving 61.7 grams of C3H7OH in 175 milliliters of water. Again, just to remind ourselves here, molality is moles of solute per kilograms of solvent. This is our solute right here. So we do have 61.7 grams of C3H7OH. We want to convert it into moles, so it will require us to go to the periodic table and add everybody together. That's going to be 3 times 12.01 plus 8 times 1.008 for the hydrogens, and a 16 there for the oxygen. That's going to give us 60.09 grams per mole. That's going to give us 1.03 moles. And this would be the top part. In this case, the water is the solvent, right? And we're given that it's 175 milliliters, and the density of water is 1 gram per milliliter. That's what's going to convert us into grams. So it's a pretty simple calculation there. 175 milliliters. We're going to multiply it by 1 gram per milliliter. That's going to give us 175 grams of water, which is our solvent. But when we do molality, we don't want grams, we want kilograms. So there are 1,000 grams in a kilogram, right? Grams cancel, milliliters cancel. And that's going to leave us 0.175 kilograms. And that is really the bottom part here. So what's left to calculate the molality, we're just going to plop those numbers in there. So we're going to take 1.03 moles over 0.175 kilograms. And if we do that, 5.87. Now, in terms of the units, much like molarity, you could leave it as moles per kilogram. The number always stays with the moles part. It's always 1 kilogram. Or like molarity, you could just write 5.87 little m as well. So you do it either way in terms of the answer. Any questions on that calculation there? Okay. Now, mole fraction, we talked about when we did gases. So this is the same mole fraction as what we saw earlier. And that is we add up all the moles that are present and we divide the moles we're interested in by the total moles. So remember, mole fraction is that X. And basically you take the moles of A divided by the total moles in a mixture. Again, here we don't multiply by 100, which means all the mole fractions should actually end up as 1 when you add them together. Instead of 100%, 1 would represent 100% of it, since we don't multiply by 100 in this case. So that's something we saw with gases, and again, it's the same thing. And I think we might have done this problem. So just to reiterate here, if we wanted the mole fraction here for methanol, which is the CH3OH, in a mixture of methanol and ethanol, we would add up the total moles, which in this case is 0.328 and 0.929. And we would take the moles of the methanol, which we're interested in, and divide it. And at this point, if we wanted the mole fraction for C2H5OH, we could do the same deal. We could do 0.929 moles divided by what you got there on the bottom, 1257 moles. And that would give us our mole fraction. Or if we wanted to, we could just take 1 minus that, since it's 100%. That should be the only thing that's left. And we'll get something like 0.739 as the mole fraction for the ethanol in this case. So again, that's something that we saw with gases, same mole fraction, and you would calculate it the same way. I hope you do remember this one as well. This is molarity, which obviously is the most common unit of concentration. Again, that is our big M, which is moles per liter. And usually what most solutions in terms of concentration are given to you as. I think we might have touched upon it as well. Tactically, molarity could be millimoles times milliliters. Again, where you would run into that is if you decided to take milliliters times molarity, what you would get is actually millimoles, not moles. As you normally would take liters times molarity, that will give you moles. And sometimes that's okay, especially like in that dilution equation we learned, which is not D. We'll try M1 V1 equals M2 V2. If you remember in that dilution equation, you did not need to convert the volume into liters. You could, but you did not need to. And the reason you did not need to is because when you multiply milliliters times molarity, you got millimoles. And then if you did divided it by milliliters, the milli and the milli will cancel. And you'll be back to moles per liter, which again is molarity as well. Any questions on sort of solutions, concentrations, or any of that stuff? All right, so now we're going to kind of put together some of that, those ideas and some of those concentration units, some of those new ones, maybe like molality, along with mole fraction. And we're going to talk about the colligative properties of solutions. So colligative properties basically means that it is affected by the number of particles in a solution. And typically what we're talking about here is, for example, if we just had good old H2O here, right? And if we just had H2O in the solution, which is not a solution, it'd be a pure liquid. And for example, if we decided I want to heat this up, basically what we got going on is our water molecules, they are free to go, basically, right? They just, get enough energy, get enough pressure built up, and they basically can start to evaporate and escape really well. But what colligative properties means is if you take something like water, for example, which is like a pure solvent, and if you take something like water, a pure solvent, and in addition to the water, you decide, I'm going to dissolve some sodium chloride in there. So you got some sodium chloride in there. And now what's going to happen when you decide, I want to heat this up, for example? The water molecules in there, in the solvent, are really no longer have a free run to the surface, right? Just so you could kind of visualize it, they got to kind of work their way around, things are in their way. It takes a little bit longer for them to, sort of get away and get out of the solution. And depending on the number of particles that you put into the solution, it could have a drastic effect on properties of solution, things like boiling points, things like melting points or freezing points, things like vapor pressure. So by dissolving some type of particles, these could be ionic particles like sodium chloride, these could be covalent particles like, sugar or something of that nature. But they essentially get in the way of the normal way that things can boil, things can freeze. They would also get in the way of things freezing. So in water by itself, basically these water molecules, if you cool it down, are kind of free to, find each other and come together. But over here where we have the sodium chloride, same thing happens. Perhaps you got a water molecule over here, another one over here, and it's got like this big sodium in the way to find each other. So it affects, things like how they freeze or their freezing point temperature. So that's what we're going to talk about here. We're going to talk about some of the effects that occur based on the amount of particles that we see in a solution. So one sort of effect is what is known as vapor pressure lowering. Vapor pressure, if you remember, is the pressure of a gas above a liquid, right? So it's the pressure of gas molecules above a liquid. And the greater the vapor pressure, that means you have more gas molecules out of the liquid or above the liquid. And that means that that substance would be very volatile, which means it could go into the gas phase relatively easy. So the vapor pressure of a substance depends not only on the nature, but also on the temperature. And this is what is sometimes referred to as Raoult's law. This is P is equal to X times PZ, where the PZ is the vapor pressure of the component in the solution, and P with the little circle, which is a knot, is the vapor pressure of the pure substance, and X in this case is our mole fraction. So this is our mole fraction. This is sort of the vapor pressure of the pure substance. And this is the vapor pressure of the component that's in the substance. And the vapor pressure lowering is defined as the vapor pressure of the pure substance minus the vapor pressure in the solution. And that's what the name sort of implies. Vapor pressure lowering means that when you start to put some of these guys in there, what you will see is the vapor pressure will go down because all these particles are getting in the way of basically the gas being able to escape the liquid portion, and it's going to lower that vapor pressure. So let's take a look at an example here. The vapor pressure of ethyl alcohol is 66.5 torr. Calculate the vapor pressure of ethyl alcohol in a solution if 0.2 moles of glucose are put into it with 1.25 moles of the alcohol. So we're going to get the vapor pressure of the alcohol. So we're going to find the vapor pressure, the mole fraction of the alcohol. So that is the moles of the alcohol. This is the total moles, which you get from the 0.2 and the 1.25. So we're looking for the vapor pressure again here of the alcohol. And that's going to give us our mole fraction of 0.62. That is what goes here. The vapor pressure of ethyl alcohol in sort of its pure form was given to us here, which would obviously be a table value. So you can put it in, and what we see is the vapor pressure of the ethyl alcohol that has the glucose in it drops to 57.3. So just visually, if you want to sort of visually think about what's going on with the ethyl alcohol in there by itself, those molecules are free to sort of escape to the surface, no problem, creating more gas above the liquid and more vapor pressure. But once we take our ethyl alcohol and we put some glucose in there, we got all these glucose guys around. Again, they just kind of physically, if you will, get in the way of those guys being able to sort of escape the surface, and we would end up with less gas molecules above the liquid, and that results in our vapor pressure lowering in this case. Any questions on that calculation? Now, a very big sort of effect that particles have on things is what is known as freezing point. So the freezing point is where something would obviously normally change from liquid to solid. So for example, for water, that is 0 degrees Celsius. So again, the addition of any type of particles are going to get in the way of the natural process of something like water just being able to come together and hydrogen bond. Now, when you put those particles in there, it gets in the way, and it causes the freezing point actually to be lower in that case. So we're actually going to lower the freezing point. And this is the equation for freezing point depression. And a couple of things, this is the change in the freezing point temperature. And because the solution will actually freeze at a lower temperature in this case, what you want to do is when you do the change in temperature, you want to do this. You want to take the solvent, the temperature where the solvent normally freezes, minus the temperature where the solution is freezing. So you want to go solvent minus solution when you're using the change in temperature of the freezing point. Otherwise, if you don't do it that way, you will get the negative sign when you should have a positive. You will get a positive when you should have a negative, or you may add when you should be subtracting, or subtract when you should be adding. Kf is a constant, and that is a freezing point constant. That is a value that you would look up in a table. And the important part when you look it up in the table, and people oftentimes have problems with this, they go to the table and they try to find the solution. To say you had a sodium chloride solution, you try to find sodium chloride in the table, you will not find it. The freezing point constant is based on the solvent. So if this is an aqueous solution and the solvent is water, you would want to go to the table and find the freezing point constant for water, not like sodium chloride, for example. So that's really important. And M here is our molality, as we just talked about. And that is our moles of solute divided by kilograms. Moles of solute over kilograms of solvent. Now, boiling point is also affected by the addition of particles, and it affects it a different way. It actually elevates the boiling point. So instead of where something would normally boil, so for example, water, where water would normally boil at 100 degrees Celsius, by adding particles in there, it's actually going to boil at a higher temperature, like maybe 105 degrees Celsius or so forth. It also has the same sort of formula. It is the delta TB, that's the change in boiling point temperature, equals KB times M. M again is our molality, so that's our moles of our solute, our kilogram of solvent. The KB is a boiling point constant, which you would find in the table. And it is also based on the solvent. So again, you would want to look for something like water. Remember, water will not always be the solvent, but you would want to look at it. And here, though, because the boiling point's actually going to get larger from where it started, we want to do, in terms of the change in boiling point temperature, we actually want to take the temperature of the solution, which will be higher, and minus it from the temperature of the pure solvent by itself. So something like antifreeze that we put in our car actually does both things. It actually lowers the freezing point and elevates the boiling point. And that is so when you live in a very cold environment, your engine doesn't freeze, right? All the water in your car there doesn't freeze because it lowers the freezing point of water. And by raising the boiling point when you live in perhaps a very hot climate, it will not cause your water, for example, in your engine to overboil. It keeps it from boiling because it will boil at a higher temperature. Also, another example of this type of stuff, like freezing point depression. If you've ever seen those videos or like a science sort of fair or something like that, people sometimes will make homemade ice cream, right? They'll take some ice, they'll take some rock salt, put it in with the ice, and then, you know, all the other stuff to make the ice cream. But they use rock salt and so forth to really lower the freezing point. So instead of, again, the water freezing at 0 degrees, it freezes lower than 0 degrees and thus makes a nice, tasty ice cream when you do those type of things. Here's a table, again, not from your book, but you have a similar table. But again, The important part when you go to this table, we have Kf, we have Kb, and these are the normal boiling and freezing points for different substances. So here for water, we see it's 1.86 is the freezing point constant, and we see for water, the boiling point constant is 0.152 or 0.512. Say that correctly. And you can see, though, if the solvent is something like carbon tetrachloride, a couple of things change. The constants definitely change. And more importantly, so does the boiling point temperature and the freezing point temperature. So sometimes when people do these problems, they oftentimes have water in their head. So they always think, oh, boiling point's always 100 degrees Celsius or freezing point's always 0 degrees Celsius. But again, that is really specific for water. So if you're dealing with something that is different than water, you would have a different value. So why don't you give this one a go here and sort of see what you got going. What is the freezing point of a 1.5 molality aqueous solution of ethylene glycol? We'll give you some information. That is the freezing point constant. So see what you come up with here. Take a minute or two. Okay, let's take a look here. So we're dealing with freezing point, so we want to use our freezing point depression equation here. In this particular case, they gave us the molality off the bat. If they don't, then you sometimes have to calculate it. The KF, we would go to the table and look it up. The key here is it says aqueous. So usually that's a pretty big hint that we're talking about some type of water-based solution, and water is the solvent. So again, that's why when we went to the table, we looked up the value for water. And also because water is what we're dealing with here, the normal freezing point of water is 0 degrees Celsius. So that's again how we sort of get to those numbers. So we actually could plug it into this equation. Delta TF is equal to our M, which was given to us, or 1.7, times our Kf, which was 1.86 degrees Celsius over molality. The molality will cancel each other out. And what we will end up with here is 1.7 times 1.86, 3.16 degrees Celsius. Now, you may say to yourself, okay, that's the answer. And unfortunately, that would be wrong. So again, a reminder that if you solve for delta TF, that is actually not the freezing point temperature of the solution. That is the change in freezing point temperature for this solution. And if you remember, the change in freezing point temperature, because it's a depression, is the temperature of the pure solvent minus the temperature of the solution. So if we actually want to find the freezing point of this solution, it would end up being the temperature of the solution would equal the temperature of the solvent minus the change in the freezing point temperature. Now, again, the normal freezing point of our solvent, which is water in this case, is 0. So this is going to be 0 minus the change in freezing point temperature, which is 3.16 degrees Celsius. And that means that this solution will freeze at a temperature of minus 0.3, say that again, minus 3.2 degrees Celsius. So water by itself, without the ethylene glycol, the antifreeze in there, without that in there, it would normally freeze at 0 degrees Celsius. But with that ethylene glycol in the water, it will not freeze until you hit technically a point of minus 0.32 degrees Celsius. Because of all the particles in that water, the freezing point is not able to be at 0. It actually will drop down to minus 3.2 degrees. And again, that's why for freezing point, for example, this relationship is really important, because without it, you really will sometimes not get the right sign. You really will, in a lot of cases, add where you should subtract, and vice versa. Any questions on that calculation there? Okay, so we will stop the lecture here for now. What I'm going to do is we're actually almost done here with this chapter. I think there's a few more examples to go through, and then actually that will be it for chapter 10, I believe. So what I'm going to do is we'll take a break, and about 7:15, I will open up the lab lecture or section there, meeting, and I'm just going to finish the rest of this chapter. That way we will be done with it. And again, I think there's only a few more examples to go, if I'm not mistaken. So I hope you will come back for lab to listen to the rest of it, so you'll be good to go. And that is because our next and last exam, which is exam number 4, will be 1 week from today. So that is going to be, what is that, May 28th. Yes, will be exam 4. That also means, believe it or not, if I'm not mistaken, 2 weeks from today, which is June 4th, if I'm not mistaken, will be our final exam, and it's all over. Yeah. So we have left Tuesday of next week, Thursday of next week, Tuesday of the following week, and Thursday here. So we're examining there. That leaves us 2 more lectures to go officially on Tuesdays, and we have 1 more chapter, so that's not too bad. So like I said, we're pretty much done with this chapter. We have a few more sort of examples and stuff to go through. So we'll take a little break since we've been going a little bit long here. And about 7:15, I'll open up the lab one. Hang on one sec here. The link to the lab, are you talking about the link for the lab that was put up yesterday, and all the labs should be together in the module section? If not, if you go to the announcement section for experiment 12, you will be able to link into experiment 12. Experiment 13 has not been put up yet because it has to do with these colligative properties. So that's also why I'm going to finish this chapter here in lab today. And then after lab, either tonight or tomorrow, I will post up the next experiment, which is experiment 13. And I'm going to think about what we're going to do for experiment 13. I think we may just do the post-lab questions and the pre-lab questions. I'm going to look it over, but I'm thinking that's what we're going to probably end up doing for experiment 13. But it will be all on this stuff, which is colligative properties, boiling point, elevation, freezing point, depression, and those type of things. So I think it'll be good practice for the exam this next week. Again, the exam next week should cover, if I'm not mistaken, chapter 9 and 10. Yeah, so this last chapter and this chapter. So also why I do want to kind of finish up this chapter here today. So experiment 13, which is boiling point elevation or whatever it says on there, is not up yet. It will be up probably either later tonight or most likely sometime tomorrow, and then you can do that. Oh, the link for the Zoom should also be in two places, but you can find it in the module section. There should be a module that says listen live to lecture and lab. Somewhere in there should be the link for there. If not, you could also find it, I think, under the Confer Zoom part. You can find the kind of link in there as well. But it should be in the module section as well. Other questions on that? So a couple of things, reminders. You have some lab reports coming up. So yeah, one last formal lab, which was not, should be experiment, I think, 11, if I'm not mistaken. Maybe it's the titration one of those, I don't know. And then so you have experiment 12, which is kind of fill in the papers, experiment 13 and so forth. And the last one, which is kinetics, will also be kind of fill in the papers and stuff like that. So make sure you stay up with those labs. Make sure you get them submitted when they need to be submitted. You know, we're down to 2 weeks. Yeah. So make sure you got all that stuff coming in. All right. So the exam will still be scheduled now. Again, like I said, on May 28th, with this 1 week from today, chapter 9 and 10. All right. So we'll take a little break. 7:15, come through the lab lecture link, not this one that you did for here. And we'll finish up the last few examples, and then we'll call it a weekend, I think, probably at that point. All right, everybody good? All right, I'll see everybody in a bit.